Thank you for the introduction. Hello everyone, I'm Jinwan Jung from KAIST. In this talk, I'm going to present our work of backscatter-based gateway to provide the pervasive internet connectivity for commodity IoT. This is a joint work with my collaborators. Recently, with the rise of 5G, Internet of Things, or often called IoT, is now surrounding us with various IoT devices, where the key feature of IoT is, as its name implies, the connection to the internet. In terms of its applications, for example, smart home, event detection system, and smart factory, all of them require the internet connection to provide IoT services. That means it becomes more important to connect IoT devices to the internet. Then, how are the IoT devices connected to the internet? In general, those low power IoT devices are equipped with low power RF like ZigBee, so that they are connected to the internet via multi-radio IoT gateways, which bridge the gap between the IoT devices and the internet. Although those IoT gateway is able to provide internet connections, due to multi-radio and power-consuming components, they consume so much power, such as 3 watts and 1.55 watts, compared to the IoT devices for those commodity gateway, so that they are required to be work-plugged, and it also means they cannot be freely deployed anywhere. Then, as the number of IoT devices increases, it should be followed by the gateway deployment for internet connection. In that sense, with the ever-growing body of IoT, which is battery-powered and thus can be freely deployed, whereas the limited deployment of gateway incurs blind spots so that many of IoT devices are hard to be connected to the internet. So by covering those blind spots, we want to make it possible to provide the pervasive internet connectivity for IoT. As a solution, we'd like to use backscatter technology, which enables low power and low cost communication via reflecting wireless signal in the air, and Wi-Fi devices, which are already prevalent and pervasive around us. Based on them, we introduced the first backscatter-based gateway called GateScatter. By backscattering, GateScatter translates ZigBee signal into Wi-Fi signal, where the original IoT data is preserved in the translated Wi-Fi signal, and thus it works as an IoT gateway. It means by deploying GateScatter and the Wi-Fi device, we provide internet connection to those blind spots. Since the low cost and low power characteristics of GateScatter, we can easily deploy them to cover those blind spots. Hence, we are trying to provide the pervasive internet connectivity to the massive IoT. Our GateScatter is inspired by the state-of-the-art inter-technology backscatter work of Interscatter. Interscatter studied how to read the tag data using commodity BLE and Wi-Fi. Interscatter makes a BLE device like a smartwatch generate an excitation signal, and then the backscatter tag reflects the signal into Wi-Fi so that the tag data is delivered to Wi-Fi. While previous researches, including Interscatter, have focused on the tag data, we propose GateScatter, which conveys IoT data to Wi-Fi, where the tag data is not of interest. Specifically, with GateScatter, IoT device, and Wi-Fi device, we want to deliver the IoT data to Wi-Fi so that it can be connected to the internet. To achieve this, when IoT signal is transmitted, GateScatter converts this signal into Wi-Fi, where the IoT data must be preserved. By doing so, GateScatter can work as the first backscatter-based gateway. The key challenge is how to convert this unknown IoT signal into Wi-Fi, where the IoT data should be preserved. In order to answer this question, we designed 3 key techniques. First, signal reshaping is to reshape ZigBee signal into Wi-Fi signal. Second, we propose noise reduction via in-phase suppression. And finally, Wi-Fi packet assembly is required to make a legitimate Wi-Fi packet. So let me explain the detail of each technique from signal reshaping. Signal reshaping is to reshape ZigBee signal into Wi-Fi signal. In this work, we choose the 802.11b standard as a Wi-Fi target This is because, first of all, the data rate of 802.11b is a 1 megabps, which is enough to support 250 kilobps of ZigBee. Furthermore, due to the highest SNR of 802.11b, this signal reshaping enables more robust backscatter communication. However, this reshaping is challenging because of the large discrepancy between ZigBee and Wi-Fi, such as bandwidth, complex and real signal, modulation, and so on. So to simplify the explanation of signal reshaping, let's look at the quadrature only at this time. To bridge the gap between ZigBee and Wi-Fi, we propose signal reshaping by backscatter. When GateScatter reflects ZigBee signal, it is the same as signal multiplication in the time domain. For example, this amount of ZigBee signal is backscattered by the GateScatter. Then it reshaped like this. The second part of ZigBee is backscattered with the phase shift of phi. Then it is equivalent to multiplying -1. By repeating this signal multiplication by GateScatter signal, the result signal is reshaped into the right-hand side one. Then let's look at the green Wi-Fi signal. This is a barcode code used for 802.11b, and as you can see, the reshaped red signal and the green Wi-Fi signal look similar, and thus they have high correlation. Furthermore, the Wi-Fi receiver decodes the signal as Wi-Fi if the correlation is larger than the given threshold. That is, our signal reshaping makes the reshaped signal have high enough correlation so that it can be regarded as Wi-Fi signal. Interestingly, this technique also makes it possible to preserve ZigBee data when it is reshaped into Wi-Fi signal, although the original ZigBee signal is unknown to GateScatter. For example, the ZigBee symbol 1 is reshaped by GateScatter, then it becomes Wi-Fi symbol 1. Similarly, when the ZigBee symbol of -1 is reshaped by the same GateScatter signal, it is mapped to Wi-Fi symbol -1. In other words, by GateScatter, each ZigBee symbol is converted into corresponding Wi-Fi symbol. And thus, it can work as a gateway since the original ZigBee data is transparently delivered to Wi-Fi. Next, based on signal reshaping, we describe noise reduction. In signal reshaping, we only consider the quadrature of ZigBee. However, there also exists in-phase component in ZigBee's complex signal. Since signal reshaping is performed in the passband due to backscatter operation, the reshaped ZigBee signal is also composed of both in-phase and quadrature. That is, we need to make the complex signal of ZigBee into the real signal of Wi-Fi. Here, we choose the quadrature component as a target for reshaping. At the same time, the in-phase component works as a noise. The reason to choose quadrature as a target is explained in the paper, so please refer to the paper for details. And then, to minimize the noise caused by the in-phase, we select the target of quadrature signal in the time domain. In other words, by looking at this complex signal, you can easily see that in this portion, the quadrature has high amplitude, while at those parts, the in-phase is dominant so that it may incur first synchronization to the in-phase. So our question is how to maximize the correlation to only the quadrature part while it suppresses the noise of in-phase. To answer this question, we propose signal selection for noise reduction. Given this complex signal, we redesign the GateScatter signal so that it selects the time where the quadrature has high amplitude, and we suppress the time of having dominant in-phase signal by multiplying 0 of GateScatter signal, which is equivalent to absorb the signal without backscattering. By doing this, we can obtain this reshaped signal where the correlation is maximized with quadrature and the in-phase noise is reduced as much as possible. Therefore, we make the quadrature reshaped into a Wi-Fi symbol. To demonstrate that this signal reshaping and signal selection are able to successfully reshape the ZigBee signal into Wi-Fi, We empirically measure the reshaped signal and original Wi-Fi signal in the time domain and frequency domain. As you can see, the reshaped ZigBee showed maximized correlation of quadrature and suppressed in phase, while its bandwidth is successfully expanded to mimic the Wi-Fi signal. Until this, we achieved that the reshaped ZigBee symbol becomes Wi-Fi symbol. Lastly, we present the technique to assemble a resumed Wi-Fi packet using the reshaped symbol. Our key insight to assemble Wi-Fi packet is related to the fixed headers of ZigBee and Wi-Fi. Let's see the ZigBee's packet structure first. Here, the point is its header composed of preamble and FSFT actually has the fixed bit pattern, which is known in advance. At the same time, in this Wi-Fi packet structure, it also has the fixed header from sync to PHY field. That means because both ZigBee and Wi-Fi headers are fixed and known in advance, we can assemble the Wi-Fi header from the ZigBee header by finding a map from fixed bit to the bit. More interestingly, the length of ZigBee header is only 160 microseconds, which is a bit shorter than the required header length of Wi-Fi. However, we found that the sync field of 802.11b header is fine to have a shorter length since it's conservatively designed, which is proven by our evaluation. More specifically, let's assume that the bit stream of ZigBee and Wi-Fi header are given like this. Then, using GateScatter, we can find the map from -1 to -1, which is obtained by multiplying GateScatter signal explained earlier, and that is denoted by non-invert bit. If we want to invert the bit from -1 to 1 or 1 to -1, then we can multiply the inverted GateScatter signal. And by doing this, for the given and fixed bits, we can assemble a resumed Wi-Fi header so that the reshaped ZigBee signal can be successfully received by commodity Wi-Fi. As a result, our GateScatter can work as an IoT gateway. For example, an IoT device transmits a ZigBee packet containing data with AB. Then, by GateScatter of signal reshaping, signal selection, and packet assembly, the ZigBee packet is reshaped into a resumed Wi-Fi packet, which still preserves IoT data of AB. Thus, we say that it works as a gateway. And more interestingly, our GateScatter can be applied to not only ZigBee, but also various proprietary protocols and standards based on IEEE 802.15.4.5. As explained in this talk, we only leverage the PHY characteristics of ZigBee to convert it into Wi-Fi. That means various protocols and standards on top of the same PHY of 802.15.4 can be converted into Wi-Fi by GateScatter via the same technique. In other words, GateScatter can be a unified gateway without knowing the upper layer structures, so that there is no concern on packet structure revealing, security, or privacy issues. Our design is also generalized to BLE with the similar technique, so please refer to the paper for details. In order to demonstrate GateScatter, we prototype and implement it on FPGA. We design our PCB prototype based on the open source of previous work of Hitchhike. Here is our experiment setting. As a transmitter, we use TI-CC2650, which is a multi-standard chip, and we choose commodity smart home devices to show its generality. Our prototype of GateScatter works as an IoT gateway so that packets sent by the transmitter will be received by a Wi-Fi laptop. Here, let me show you our demo video for GateScatter. In this demo, we use a smart bulb as a transmitter and the Wi-Fi laptop as a receiver. Without GateScatter, obviously, no packets are received at Wi-Fi. And by introducing GateScatter as a gateway, it converts ZigBee signal into Wi-Fi in the air. You can see the ZigBee packets are received as a Wi-Fi packets. And more importantly, we can retrieve the original ZigBee data from received Wi-Fi bits That's why it works as a gateway. Not only that smartboard, we also try many other commodity IoT devices, and as you can see, GateScatter is applied to various commodity systems as a gateway. To evaluate the throughput performance of ZigBee to Wi-Fi, we evaluate our system on this experiment map. And the evaluation shows that GateScatter can achieve the throughput up to 222 kilobps, which is quite close to the maximum throughput defined in the ZigBee standard. And it also achieves the communication range of up to 27 meters. We also evaluate the impact of interference can be caused by or to existing Wi-Fi networks. The top two figures demonstrate the throughput performance of existing Wi-Fi networks when there exists the GateScatter. We want to note that due to the small power of backscattering, it affects only small amount of interference on the Wi-Fi network by the capture effect. In the opposite direction, the existence of Wi-Fi networks impacts on the performance of GateScatter. However, we claim that the robustness of 802.11b CMO, which is converted by GateScatter, it enables reliable communication despite of the existence of Wi-Fi networks. As an application scenarios, we propose two cases. The first one is for mobile users. Carrying GateScatter and Wi-Fi device by mobile users, we can collect IoT data even from outdoor environments. The evaluation shows the performance if there exists some mobility. The second scenario is for smart home, where IoT devices are deployed in your home. Then by deploying low power and low cost GateScatter around them, we can easily connect it to the internet. Finally, let me summarize our work to give you a take-home message. In this work, we proposed the first backscatter-based IoT gateway called GateScatter. We believe it has a potential to provide pervasive internet connectivity for commodity IoT. This technique enables conversion from unknown IoT signal into Wi-Fi so that the intact IoT data is delivered to Wi-Fi. Thus, it works as a gateway. And also, as demonstrated, we prototype and evaluate it on commodity IoT devices. Thus, we present the proof of concept as a unified gateway. Thank you for listening. I'm happy to have any questions from you. So see you in the live Q&A session. Thanks again.